Rsa and Ecc Online Calculator. Rsa Online Calculator. Primes. The security of Rsa is based on the fact that it is easy to calculate the product and n of two large primes P and Q. However, it is very difficult to determine only from the product and the two primes that yield the product. This decomposition is also called the factorization of n. As a starting point for Rsa, choose two primes P and Q. Step 1. Compute n as the product of two prime numbers P and Q. The values of P and Q you provided yield a modulus n, and also a number R equals P minus 1, Q minus 1, which is very important. You will need to find two numbers E and D whose product is a number equal to 1 mod R. Below appears a list of volume of some numbers which equal 1 mod R. We will use this list in step 2. N equals P times Q. R equals P minus 1 times Q minus 1. Rsa candidates for 1 mod R is 121, 241, 361, 481, etc. Example, if P is equal to 11 and Q is equal to 13, these are the candidates for 1 mod R. 121, 241, 361, 481, 601, etc. Only with the knowledge of P and Q, we can efficiently determine pi n. The secret key also consists of a D with the property that E x D minus 1 is a multiple of pi n. Expressed in formulas, the following must apply: E times D equals 1, or mod pi n. In this case, the mod expression means equality with regard to a residual class. It is x equals y mod z. If and only if there is an integer with x minus y equals z times a. For the chosen values of p, q, and e, we get d as d equals 47. This d can always be determined if e was chosen with the restriction described above. For example, with the extended Euclidean algorithm. Step 2. Find a number equal to 1 mod r which can be factored k. Encryption and decryption. Internally, this method works only with numbers, no text, which are between 0 and n minus 1. A message M number is encrypted with the public key NE by calculating M equals ME mod N. Decrypting with the private key ND is done analogously with M equals MD mod N. This is M equals ME times D or mod N. Rsa exploits the property that XA equals XB mod N if A equals B mod pi N. As E and D were chosen appropriately, it is M equals M, the order does not matter. You could also first raise a message with the private key and then power up the result with the public key. This is what you use with Rsa signatures. Step 3. Find two numbers E and D that are relatively prime to N and for which E times D equals 1 mod R. Use the factorization info above to factor k into two numbers E and D. Consistency check. If your choices of E and D are acceptable, you should see the messages E times D mod R equals 1. E and R are relatively prime and D and R are relatively prime. Example. From the chosen we choose from step 1 E equals to 241, D equals 121. So the output should be E and R are relatively prime and D and R are relatively prime. Step 4. Use E and D to encode and decode messages. Enter a message in numeric form Break your message into small chunks so that the message codes are not larger than A. Rsa Online Calculator. Elliptic curves. An elliptic curve comes from setting a quadratic in y equal to a cubic in x. For example, y squared equals x cubed minus 3x plus b, where b is a large integer constant, was recommended for government use by NIST as p minus 256. Y squared equals x cubed plus 7 is used by Bitcoin. It's from the Standards for Efficient Cryptography, or SEC, group name SECP256K1. X and Y are chosen from a field. Elliptic curves are actually not too interesting over real numbers, but they have really interesting and useful mathematical properties when X and Y are restricted to integers, rational numbers, or finite fields. Mathematics of elliptic curve addition and multiplication. Curve point addition on elliptic curves is defined in a very weird and interesting way. To add two curve points, x1 and y1 and x2 and y2, we 1. Draw a line between the 2 points. This makes our operation commutative. 2. Intersect the line with the elliptic curve. This makes our operation's outputs be a curve point. 3. Mirror the intersection point about the x-axis. This makes our operation an interesting group. Addition is step 1. Draw a line between the 2 points. One equation for a line is y equals m times 6 plus b. Note we are loading using b above, so we switch to b for the constant. Step 1a. Draw a line between 2 points. The slope of the line is m equals dy dx equals y1 minus y2 and x1 minus x2. Step 1b. Draw a tangent line at one point. If you're adding a point to itself, you don't have 2 points to take a finite difference, so you take the infinitesimal slope dy dx for the p minus 256 curve above. Y squared equals x cubed plus ax plus b. The total derivative is 2y dy equals 3x squared dx plus a dx, which rearrange to m equals dy dx equals 3x squared plus a and 2y. In either case, if we would divide by 0 while calculating m, we instead give up and say the sum is a special identity point, also known as a point at infinity, which plays the role of O, the additive identifier. We can use the slope to solve for the y-intercept. V equals y1 minus m times x1. We now have the coefficients m and v for the line between the 2 points. Addition is step 2. Intersect line and elliptic curve. We just need to find the point xy that lies in both the line and the curve. Y equals mx plus v on the line. Y squared equals to x cubed plus ax plus b on the curve. Step 1 is to square the line equation. Y squared equal to mx plus v equals m squared x squared plus 2mvxv plus v squared. Since y squared is also on the curve, we have m squared x squared plus 2mvx plus v squared equals x cubed plus ax plus b. Collecting terms into the right side, we have O infinity equals to x cubed minus m squared x squared plus a minus 2mv x plus b v squared. This is a cubic polynomial in x, and it is actually fairly nasty to solve via the general cubic Cardano's method. But amusing, there are exactly 3 solutions. You can always write the polynomial in this form, exposing these roots. Infinity equals x minus x1 times x minus x2 minus times x minus x3 equals to x cubed minus x1 plus x2 plus x3 x squared plus x1 x2 plus x2 x3 plus x1, x3, x minus x1, x2, x3. x1 and x2 are our input points, which are known. x3 is our output intersection point because these two polynomials are equal by matching the coefficient on the x squared term we have. x1 plus x2 plus x3 equals to m squared. So, x3 equals m squared plus x1 minus x2. Now that we have x3, we can calculate the y-coordinate of the line curve intersection from the line equation. Not quite, y3 is equal to m x3 plus v. Addition is step 3. Mirror the intersection point. To make the operation work correctly, we need to flip this intersection point around the x-axis. This is easy. Just make the y-coordinate negative. y3 equals minus mx3 plus v. Hot set, we now added xy, y1, and x2, y2. To give a new on-curve point, x3, y3, the bottom line to add points, x1, y1 to x2, y2. Different points. M equals dy dx equals y1 minus y2 divided by x1 minus x2. Same point tangent. M equals dy divided by dx 3 times 3x squared plus a divided by 2y. V equals y1 minus m times x1. X3 equals to m squared minus x1 minus x2. Y3 equals to m minus mx3 plus v. From this point addition, primitive operation, you can repeat it to build multiplication, preferably using something smart like the bitwise peasant multiplication to get decent performance for large numbers. The beautiful part about elliptic curve point addition is its commutative and associative. This means we can perform Diffie-Hellman-Key exchange or any other crypto operation that relies on commutativity or associativity. For performance, rather than doing division and the slope calculation at every step, high-performance elliptic curve implementations use a three-coordinate Jacobian point representations x, y, z, where x equals to y divided by z2 and y equals y divided by z3. This produces a point addition function with several more multiplications but no divisions until you extract the final xy. Rsa Online Calculator System Modes. Represent a general elliptic curve of this form. Y squared equals to x cubed plus ax plus b. All arithmetic is modulo the prime. So this is the codes for represent a general elliptic curve. So this is the codes for the starting point. Then this is the find generator point, build square root table mode. This is a find generator or starting point on the curve. This is a prime field division, return AB mode P, and faster algorithm extended Euclidean algorithm. This is the line operation, elliptic curve point building, and verify this lies on the curve. This initialize image to white and darken pixel sitting on the elliptic curve, so on. This is the last one. Write the image data.